Hi, welcome to the lecture number 60 of fuzzy sets, logic and systems and applications. Today in this lecture, I will discuss Takaki, Sujeno and Kang fuzzy model. This model is in short known as TSK fuzzy model or TS fuzzy model. So let us first understand the TS fuzzy model or TSK fuzzy model as it was introduced by Takaki, Sujeno and Kang in 1985. And a typical fuzzy rule in a TSK fuzzy model has the form of if X is A, and then we have some connective either and or, and then next antecedent y is b. So here we have the premise and then we have the consequent. So the fuzzy rule for TSK fuzzy model is of the form of it has the premise part and the consequent part. So premise part remains as it is or as it was in Mamdani, Larson, Tsukamoto. So here also the same, means the premise part is fuzzy. It may have either single antecedent or multiple antecedent. Whereas when it comes to the consequent part, here there is a significant difference. What is this difference? Difference is this. So in TSK fuzzy model, we have the output in terms of a polynomial. The polynomial is here, and this polynomial is of the form of fxy, means function of xy, if x, y are the inputs. So let's say we have two inputs here. First input is x, the second input is y. So f of xy, which is a function of x and y, and this is a polynomial of the form of p0, which is a constant, plus p1 into x plus p2 into x square plus and dot dot plus pm into x raised to the power m plus q1 y plus q2 y square plus dot dot plus qm y m. So here in this polynomial we have a constant which is p0, and then we have the x terms. So we have first degree terms of x and y like p1x, q1y. Then we have second degree terms p2x square, q2y square, and so on. So here in this polynomial we have the mth degree or m degree terms. So in general we are writing fx y as the m degree polynomial. So the rule that is used here is a two input rule, or I would say two antecedent rule, whereas in general it can be a, any number of, it can have any number of antecedents. So what we have to remember here is that in TSK fuzzy model, the consequent part has the output which is always in the form of a polynomial, and this polynomial is in the terms of the inputs that are fed in the premise part. So here, since x and y are the inputs, which you can see in the premise part here, so the polynomial is always a function of x and y, which is nothing but the function of the generic variables x and y. Now, here, this is very important to note that a TSK fuzzy model takes comparatively lesser computation time, because here the z can be obtained very quickly just by substituting the values of x and y. So this takes very less time of computation. And then TSK fuzzy model takes only crisp values as the input. So please note here, there is very important point, like in Mamdani model, Tsukamoto model, Larson model, all of the models we have had the inputs in the form of fuzzy or crisp. But here in TSK fuzzy model, we always have the inputs, that means the x and y, only crisp values. So then we have the each rule has a crisp output in terms of the f of x and y, as I have just explained. And then, since every rule is generating some output, so the overall output of the TSK fuzzy model, which is characterized by multiple rules, will be the weighted average of these outputs. So here we can have f, the function, the polynomial, as a constant, and if we have such a case, then we say this as the zero order TSK fuzzy model. We'll discuss this in detail in coming slides. We have explained this, and then when fxy is a first order polynomial, the resulting fuzzy inference system is called first order TSK fuzzy model. The zero order TSK fuzzy model is a special case of the Mamdani fuzzy model, in which consequent part of each rule is specified by a constant value, which can be represented by a fuzzy singleton, as we already have seen. In the beginning of this course, we understood what is a singleton, fuzzy singleton. So constant can also be represented in terms of a fuzzy singleton. And then the special case of Tsukamoto fuzzy model, in which the consequent of each rule is specified by a membership function of a step function centered at the constant. So that way, the zero order TSK fuzzy model can be understood. And here in zero order TSK fuzzy model, if we go ahead to understand, we see that the fx y or f of x y is a constant value, that is p0 here. Then, so since we have, let's say, the ith rule in TSK model, let's say we have a set of rules and ith rule is here, is ith rule. So ith rule will have the rule of this kind: if x is ai, x is the input, ai is the fuzzy region where this x is falling into, and then we have the connective here, and or, and then we have another input y, and which is again falling into bi. I here signifies that the fuzzy region which is relevant for ith rule, and then we have the premise part, which is Zi for ith rule, the output for ith rule, and this is nothing but a polynomial which is f of x, y. So here we may have a TSK fuzzy model which can have n number of fuzzy rules, small n number of fuzzy rules. So if this is the case, then for AI to be a fuzzy set here, BI again to be a fuzzy set, continuous fuzzy sets, and if this is the case, then for certain input x and y, we can have the Wi, which is nothing but the firing strength of the particular ith rule. So I can write here the firing strengths of ith rule, and this we can obtain by either taking min of mu ai x and mu bi y, or we can multiply these two if we are interested in the product. So here, since these firing strengths are of each rules are known, then we can go ahead for the final output by taking the weighted average of the each rule. So this way we find the final output of the TSK fuzzy model. So let us now start with first the zero order TSK fuzzy model. So as I have already mentioned that the consequent part here in TSK fuzzy model, the fuzzy rules will have the consequent part of this kind. The output, basically the Z, will be defined in terms of f of x comma y. As I have already mentioned, this x and y will be the corresponding generic variable, generic input variables. And when we talk of zero order TSK fuzzy model, then it means we will have only the constant, that is P0. So here we have the P0 only. So fx y, or I can say f of x comma y, will be equal to only the constant part, that means the P0. So this is the constant part. So no x term, no y term. So this means that the zero order TSK fuzzy model output will not depend on the generic input variables, here in this case x and y. So let us now go for the fuzzy reasoning of zero order TSK fuzzy model, and we have three cases as we have had earlier for other fuzzy models. So we have the first case where the single rule with single antecedent type of TSK fuzzy model we have, and let us now first go with this and understand as to how we are going to get the output computed if we have a TSK fuzzy model with single rule with single antecedent. So as I've already mentioned that we can have only the crisp input. So here x is equal to x1 we are supplying. So the fact or the input we can have as x is equal to x1. And here is the rule. We have only one rule. So only one rule is mentioned here. And rule has the single premise, single antecedent. So single antecedent is here x is a. And then we have the consequent part, and consequent part is f x comma y, means f of x and y, which is the P0 here, and which is a constant value, means it is not depending upon the input generic variables. That means here in this case we have x. So let us move ahead and see how can we get the output computed with respect to the certain input that we feed to the output. So let us assume that we have x1, which is the input variable, input generic variable here, 2.0202. Let's say we have this value and we are feeding this value to this model, to the TSK fuzzy model characterized by the single rule with single antecedent rule, fuzzy rule, which is mentioned here. If x is a, so x is here, so I can write here the rule that is characterizing this model is if small x is a, then the output here in this case, let's say y. So y is f x y, or maybe since we are using y, so I can write here z. So z is equal to the output is p0, or if we use y it is better. So let's say y, which is the function of fx, because uh, we have only x in the premise part as the single antecedent. So here we have a constant, and constant is p0. So this is what is the rule which is characterizing, which is representing the fuzzy, the TSK fuzzy model. So if this is the case now, and please note that we have a and P0 both are known for this model. When we say we have a model, it means all these parameters of A and P0 are known. So let us now apply the input here. So when we apply the input, we see that corresponding to x1, we have the membership value here, which is coming out to be 0.5204. So here, so this is the intersection point, and this I can write as W1. So since we have only one antecedent, min is not applicable here. So the same value will be transferred to the output here for the weighted average. So W1 is known. Now how we will have the y1 corresponding to this rule? So let's say y1, if we are supplying x1, corresponding output is y1. So y1, since the so y1 will be 3.737, which is same as p0, because this output is not depending upon the input. So we have the y1, and now the final output will be the same even when we do the weighted average. So you see here we have done the weighted average. Since we have single rule, so the weighted average is going to remain the same. So this way the output corresponding to x1 is equal to 2.0020 will be 3.737. Alright, so now the next case here for the zero order TSK model would be where we can have a single rule but with the multiple antecedents. So let us now go ahead with this case here. So here also we have, you see, the zero order, and zero order means the output is a constant. The consequent part is a constant. Consequent part means the output of every rule is a constant and which is not depending upon the input generic variables. So here also we have P0. So, but what is the difference here is that we have two antecedents. One is the X is A and the other one is here. The other one is Y is B. And these two antecedents can be joined by a connective. Here we have AND. So this is the connective. Please note that this connective can be OR as well. So we can have any other connective. So here in this case we have AND connective. So now since we have two antecedents, so obviously here we have two input generic variables X and Y. Now when we have the input and we are now applying this input and we are interested in finding the corresponding output. Now let's see how to proceed with this. So let us assume that we have x1, the input value, which is a crisp value, x1 is equal to 4.444 and y is equal to y1 is equal to 6.2626. So let us assume these two values, two crisp values as the input values. So this arbitrary value, you can have any other value. And please remember that we take only those values which are going to intersect the fuzzy sets A and B. Why? Because otherwise these inputs, these fuzzy regions may not be relevant and this rule may not be applicable. So this is the rule in this case here, where we have if X is capital A and Y is B, capital B. So in this case we have the output which is P0. So here also if we apply this, these two inputs, so let's see now how to get the W11 and then W2, W12 as the intersection points corresponding to X1 and Y1 respectively. And here we are taking min. Why we are taking min? Because we have the connective AND. So connective in between the two antecedents we have AND, so that's why we are taking min here. If we would have OR connective, then we would have taken max. So for AND connective we could have also gone for product. So it is up to us what we want or what is needed to be what is the preference. So if we take the minimum of here the W11 and then W12. So when we take minimum, we are going to get the W1 is equal to here, W1 is equal to 0.1868, which is the lowest value. And since we have W1, we have Z1 here, and Z1 is nothing but the here the Z1 is Fx1 xy and which is nothing but P0. So we can very easily say that Z1 is P0 and Z1, since Z1 is P0, we have now Z1 is equal to 3.737. So we now know the W1 and Z1. So now since we have only one fuzzy rule here, only one rule, that is in this case we have, so the weighted average is going to give us the same output here because we have only one rule. Had it been many rules or more than one rules, then the output would have been accordingly computed. So let us now go for the third case where we have multiple rules with multiple antecedents. So here you see, for simplicity, we have two rules, first rule, second rule, and then we have multiple antecedents. Here we have only two antecedents. We have taken two antecedents for simplicity. So otherwise we could have taken any number of antecedents. Rest other things remain the same. So we have two antecedents and the connective is AND. So let us now proceed with this model having two rules and two antecedents. So let us apply. So we have the rule number 1 here and we have the rule number 2 here, and we are now giving the input to the model. So, and please remember that this model, this input is the crisp input, you can see. So any arbitrary input which falls within the fuzzy region can be, fuzzy regions of A1 and B1 can be taken, A1, B1, A2, B2 can be taken, or else it may be given as the unknown input suitably. So for x1 is equal to 6, y1 is equal to 8.2, let's now find first, using first rule, the W11, which is the intersection point. So intersection point, let us call this as W11, and this is coming out to be corresponding to x1 is equal to 6. It is cutting A1 at 0.93 membership value. So this becomes our W11. Similarly, let us now find the corresponding to Y1 8.2 value, the intersection point on B1. So let us call this as W12. So this is our W12. Now we have W11, W12 both. Now let us take min because the connective is AND. So when we take min, our value is going to be W1, which is also called as the rule strength, or I can write here, or I can say here, the firing strengths of rule 1. So firing strength of rule 1 is W1. This is also called weight of the rule. So this is 0.78. Now P01 we already have as 8. This is a constant value. So we write it by P0, and P0 is the constant value, and 1 we are writing here for rule number 1, for rule 1. So that's why we have also used 1. Similarly here for rule number 2, P2, P02. Alright, so now we have obtained W1 and Z1. So Z1 we have very quickly found. This is XY, which is P0, 1. Here in this case, let's say this is here in this case, Z1. So Z1 is P01. Similarly, now on the same lines, when we use rule number 2, we find the intersection point, that is, let's say W21 for the second rule, first antecedent, and similarly here for y1 is equal to 8.2, we write here W22. So W22 means we second rule, second antecedents. Now both of these values are 0.99 and 0.13, and when we take min of the two, we are getting the firing strength of rule number 2. So we have firing strength of rule number 2, which is coming out to be W2 is equal to 0.13. And second rule gives us P02. So P02 is giving us 6 already. So Z2 will become 6 here. So I can write here that our Z2 basically is F2xy is equal to P02. So this way we get Z2 is equal to 6. So now we have W1, Z1, W2, Z2. Now we can very easily find the weighted average. So let us find the weighted average of the outputs of each rule, and when we use this formula for weighted average, the Z star, which is the final outcome, the weighted average of the output, we are getting 7.7143. So this way we can find the the final output corresponding to x1 is equal to 6, y1 is equal to 8.2 using the TSK fuzzy model, which is characterized by two rules with two antecedents, and this comes under the category of multiple rules with multiple antecedents. Now let us move to the first order TSK fuzzy model. So as I have already mentioned, the order basically is defined here with this, with when we talk of first order TSK model, it means the input generic variable, at least the maximum power of these input cannot exceed 1. So this means what? So the output of each rule will be of this form only. So P0, the constant can be there, P0, and then P1x. This P2x cannot be there. Similarly, no higher terms cannot be there. No higher terms can be there. Or the higher terms cannot be. Higher terms of the input generic variables are not there. Similarly, for y also, only since this is first order TSK fuzzy model, so only y will be there, y raised to power 1. So more than 1 cannot be there. So what is coming out to be here is that f x y, which is the form of the output of each rule. So f x y, let's say for two input generic variables, so we can have p0 plus p1 x, and then we write here q1 y. But since there is no other variable, so I can write here p2 y. So that is how this is of this form. So first order TSK fuzzy model will have the output, the consequent part, that means the output of this form for two inputs. If we have only one input, then obviously this y term will go away. So along with the constant, we will have one more term, and this term will be the one more term for the single antecedent. But similarly, if we have multiple antecedents, we will have multiple antecedents. But the power of the degree of, the power of each generic variables, the input generic variables cannot exceed more than 1. So let us quickly go ahead and understand. So here this is mentioned, this is the general form of the polynomial of the output here. of first order TSK fuzzy model, but here m cannot be, m can be only 1. So m, value of m can be only 1. So I can write here the, when we say first order TSK fuzzy model, it means m is equal to 1. The value of m is equal to 1. Similarly, when we say 0, this is for first order. Similarly, m is equal to 0 for 0 order. So m is equal to 0, 0 means 0 order. What does this mean? This means that only constant will be there. So now, as I mentioned, then the output will be like this. Similarly, all other terms and conditions will remain the same, means we have the min if it is needed for the connective and, or we'll take max in case of the or connective, and similarly we will have the weighted average we have already done. So this way we proceed, and now let us, under this first order TSK fuzzy model, let us discuss all those three cases we just have discussed. So the first case again is the single rule with single antecedent. So when we have the single rule with single antecedent, we have the single antecedent here, and please note that here for the first order TSK, first order TSK, we have m is equal to 1 only. This means that we have fx is equal to p0, the constant term, plus p1x. And now, if we have the rule of this kind, let's say we have a TSK fuzzy model which has the polynomial, the fx, like this. This is, let's say, z, which is the output, and this is of this form, 1 plus 0.5 into x. So if this is the case, then let us apply some input, and let us apply the crisp input x1 to 0, 2.02020 So this is the same input which we have applied in the previous previous category, that was the 0th order, and that was again for single rule with single antecedent. So we get the W1 here, and since there is no connective, only one antecedent is there, single antecedent is there, so this becomes the W1. So this becomes the W1. So this is the weight of the rule or firing strength of the rule, so W is known. And then our Z1 will be 1 plus 0.5, 1 plus 0.5 x. X we already know because we have applied this, so 1 plus 0.5 into 2.0202. So this way we get the total here is 2.0101. So we have now Z1, and since we have only one rule, we have single rule, so the weighted average is not needed, or even if you go for this, that is going to remain the same. So this way we get the output of the TSK fuzzy model, which is characterized by single rule with single antecedent, and when we apply the input x1 2.0202, we are getting the output here. We are getting the output 2.0101. Alright, so now Let us go to the second case of first order TSK fuzzy model, where we have a single rule but with multiple antecedents. So here also, for simplicity, we have taken only two antecedents. X is A and Y is B. But these two antecedents are connected by the connective AND. And again, I would like to mention that this connective can be any connective, can be OR as well, or but, or whatever. So here, since we have AND will have the composition of min. So we'll use min. If we would have OR here, then max would apply as the composition. So AND is the connective here. So rule says if X is A, the first antecedent, and then we have the connective, and then we have the second antecedent, Y is B. So then here the output is of the same type which we have just discussed, and this category is the first order TSK fuzzy model. Now, when we and before this, I would like to mention that the here, for simplicity, we have taken the two antecedents, but we can have any number of antecedents. Now let us go ahead and apply some crisp inputs x1, x and y1. And since we have here the single rule, so let us apply this to a TSK model which is characterized by a single rule with two antecedents. X is A, Y is B. So we see that here we are applying the same inputs as we have done in the zero order TSK. So x1 is equal to 4.4444 and y1 is equal to 6.2626. So we see the corresponding points of intersection, and this is designated as the W11, and then this is also designated as W12. Now within these we take the min because we use the connective AND. If we would have used OR connective, then here we would have taken max. So this gives us the again the firing strength of rule. It is also called weight. So we have the Z1 because we have the first order polynomial equation here, which is the output. And please note that since we have here two antecedents, so that's why the Z is in terms of X and Y. So we see here the X, Y, which is nothing but the output, let's say Z, and this is of this form. P0, P1, X plus P2, Y. So this is how we are getting the Z calculated for this. So, and this is nothing but the Z1. So here what is Z1? Z1 is this. So Z1 corresponding to X1, Y1. And P1 is known, P0 is known, P0 is known, P1 known, P2 known. So, and W1 is also known. So we can quickly get Z1 corresponding to X1 and Y1. And since we have again here the single rule, so the output is going to remain the same. So the weighted average, even if we take here, is going to be 3.5747. So this is equal to Z1. Now, the third case is multiple rules with multiple antecedents. So let us now take two rules under this case for simplicity, rule number 1, rule number 2, and both the rules have two antecedents again for the simplicity, and is the connective as I have mentioned. So here the output also remains the same as we have seen in the previous cases of first order TSK fuzzy model. The only difference that we have here is because we have two rules, so we have differentiated, we have written Z1 and Z2 for the corresponding rules as the outputs. Now let us use these two rules, rule number 1 and rule number 2, to generate the outputs corresponding to the inputs, crisp inputs supplied. So let us apply the input x1 and y1. x1 is equal to 6, y1 is equal to 8.2. And let's see the corresponding outputs. So corresponding to rule number 1, the W1 is the points of intersection corresponding to x1, the first antecedent, first input. So we find here the W1, 1. And then we have here in rule number 1 the points of intersection here for the second antecedent for y1 is equal to 8.2 is W1, 2. Similarly, when we use rule 2, we get this as this intersection point corresponding to x1 is equal to 6 as W2, 1. Here for corresponding to y1 in rule number 2, for the second antecedent we get the point of intersection as the membership value and which represents the W2, 2. Now let us use rule number 1 output here. So let me first write the Z is of the form of, the output is of the form of x, y, and then we have P0 plus P1 x plus P2 y. And since the Z1 is given for the first rule, Z2 is given for the second rule. So now if we use the x1 and y1, this is x1, y1. So if we use x1, y1 values, which is the input, set of inputs, which is the input x1, y1. So then we get Z1. So we see that we get the Z1 here, which is 4.74. So when we use x1 is equal to 6 and y1 is equal to 8.2, using the first rule output, we get Z1 is equal to 4.74 here. So similarly, now we use rule number 2 and find the Z2. So here on the same lines, when we use the input here, so x1 and y1 we use as the input. So Z2 for the same x1, y1 we are getting as the Z2 is equal to here 2.34. You can see here. And how do we get this? We already have Z2 is equal to 0.02 plus 0.25 x1 plus 0.1 y1. So please understand here that this Z1 is like this. So Z1 is here, Z1 is F1 x y, and this is of this form, P01 plus P1x plus P2 1y. Similarly, our Z1, Z2 is of this form. Our Z2 is F2 xy is equal to P0 2 plus P1 2x plus P2 2y. So here we have Z1, Z2, and we also have W1 and W2 by taking the min of the corresponding weights, corresponding membership values. Now, since we have two rules here and corresponding to each rule we have its outputs, now we take the weighted average of it to get the final output. So final output we use here the weighted, we take the weighted average, and this way we get Z is equal to 4.3971. So this way, if we have a TSK fuzzy model which is characterized by the set of rules, set of multiple rules with multiple antecedents, then we'll proceed with this kind of. And then here let us take an example to understand the TSK fuzzy model better. And this example is basically a first order TSK fuzzy model, and which is having 4 rules you see here. So we have rule number 1, we have rule number 2, 3, 4. So all the rules have the outputs that are different. So I can write here, this is the Z1, this is Z2, this is Z3, this is giving us Z1, Z2, Z3, and so on. This is giving us Z4. So when we have a TSK fuzzy model and this is characterized by 4 rules, and we see that each and every rule is coming under the category of the first order TSK fuzzy model. So, and then we see that the fuzzy regions that are mentioned here in the rule A, B, they are basically having 3 fuzzy regions. They are having 3 fuzzy regions, and each fuzzy regions are represented by the fuzzy sets which are represented, which are characterized by the membership functions mu a low, mu a medium, mu a high, and mu a low is Gaussian, mu a medium is triangular, mu a high is trapezoidal. Similarly, the input in the antecedent part is divided into 3 fuzzy regions, and every fuzzy region is defined by or represented by fuzzy set low, medium, high, and all these fuzzy sets are characterized by the membership functions mu b low, mu b medium, mu b high. And you can see the mu b is trapezoidal, mu b medium, mu b low is trapezoidal, mu b medium is also trapezoidal, mu b high is also trapezoidal. So what is that which we need to do is, here we have to calculate the output for the inputs x is equal to 70, and please understand here the connective that is mentioned here is R. So here also you see the connective, instead of and we have R. So if we have this kind of situation, we know what to do. So we have the inputs x is equal to 70 or y is 60. So let's now proceed with this. So first of all, what we do, we plot all these membership functions, and these membership functions basically designate the fuzzy sets low, medium, high, and similarly for the output as well. Now both the inputs, so first input here and then second input here, means the first input means first input variable, first input generic variable, second input generic variable y here, and both the inputs are now plotted, and we have the membership functions here. And now our task is to find the intersection points. So first of all, corresponding to this input, the input that is given, so our input that is given is x is equal to 70 or y is equal to 60. So corresponding to x is equal to 60, when we plot this, we see that here this x is equal to 60 falls under two fuzzy regions. First fuzzy region is this one, the high region, which is basically the high fuzzy set, and the other one is this fuzzy region. This is a Gaussian. This is represented by Gaussian. So low fuzzy region is also coming into picture, and low fuzzy region here is very less, because this is represented by a Gaussian fuzzy set, Gaussian fuzzy membership function. So there are two regions which are relevant for x is equal to 70. Similarly, now let us check for the y is equal to 60. So for y is equal to 60, we see that only one fuzzy region is relevant, that is high. So for y is equal to 60, we have only high fuzzy set which is relevant. So we see that we have two points of intersection in the first antecedent, that means the first input generic variable, and the y is equal to 60, we have only one fuzzy region which is relevant. So 2 into 1 is going to give us two combinations. What are those two combinations? First is high, 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 and then high. So both the inputs basically. So when the input is falling in the, I'm writing here as the, when x is falling in high, and then y is falling in high, then what is going to be the z, the output? So this will get by inspecting the rules that are given to us, the fuzzy rules that are given to us. But here we have two combinations. So another combination is when x is falling in low and y is falling in high, because here only the y is falling only in high. So now for these two combinations only we need z. So let us check here. We have four rules. So first is when the input is falling in, x is falling in low. This is basically x. This is when the input is this is y, this is y, this is x, x, y, y. So when x is low, or y is high. So this combination is this. So for this, the output will be applicable is this Z1. So we can say the rule number 1, that means the Z1 will apply. And Z1 is defined by the 10 plus, the output is equal to 10 plus 0.2 into x plus 0.3 y. Similarly, the other case high high. So when x is high here, the fourth ones. So this is relevant and this is irrelevant. Means rule number 1 and rule number 4 are relevant. So high high. So output 4 here will be mentioned. So here we'll write the Z4. So this way we see that no other rule is applicable because we get only two combinations, and this can be written like this as I just explained. So rule number 1 is applicable and rule number 4 is applicable out of all the 4 rules given. This is not applicable, this is not applicable. Now take these two rules and find the output of each rule corresponding the inputs that are being supplied. So, and then whatever output that we get, we take the weighted average of it, and that is going to be the final output. So let us go ahead and do that. So here, as I've already mentioned, that rule number 4, rule number 1 and rule number 4 are applicable. So let us take rule number 1. So rule number 1 is already given. If you have any confusion, you can refer here. So rule number 1 is given, x is low, y is high. So low we already know. So low is here. This fuzzy set is low for low. So we take this fuzzy set here, low is for low. So we have to plot it. And then similarly for high, we can see from there. So high is here. In rule number 1, we have low and high combination. In rule number 4, we have high high combination. So the membership function or the fuzzy set for high high we can obtain from here. If you have any doubt, it's shown here. The high is here. This is high. So this can be very easily plotted. So let us proceed with this. So let us take rule number 1 and apply the input. So we apply the input here. X is equal to 70, y is equal to 60. So corresponding to x is equal to 60, we get here the intersection point. Let's call this as W11. Similarly, corresponding to y60, y is equal to 60, for rule number 1, let us call this as W12. W12. So W11 is 0.0022, W12 is 1. And since here we have the connective R that we have been given, so we use, instead of min, we use max. So W1 will be the maximum of W11 and W12, and which is coming out to be 1. So now we have the rule strength, the firing, we have the firing strength of the rule W1, and similarly I can write here the firing strength of the rule 1. Alright, so and Z is already given. So by just substituting the value of x and y, we get Z1 here. So Z1 is 42 if we substitute the value of x and y. So this is Z1. And similarly, when it comes to the rule number 4, we find here the point of intersection as W21 and here W22. And here also we take max of these two. So both of these are 1, 1. So we take max, and max is again going to be 1. And this is the output, which is Z2. So Z2, by just substituting this, we are going to get here this Z2. And when we substitute the values of X and Y, here we are going to get Z2 is equal to 8.8. So now we have what? We have W1, we have W2, we have Z1, we have Z2. Now we can very easily get the weighted average of these outputs corresponding to the rule number 1 and rule number 4. See here. So we have W1 is equal to 1, you can see here, and then W2 is equal to 1, Z1 is equal to 42, Z2 is equal to 8.8, and when we take the weighted average, we are getting the weighted average as 25.4. So this means that corresponding to the input X is equal to 70 and Y is equal to 60, we are getting the overall output as 25.4 when we use a TSK fuzzy model with multiple antecedent and multiple rules. So this way we quickly get to know as to how we can manage to get the final output corresponding to the inputs that are given for any TSK fuzzy model. So let us take another TSK fuzzy model which is having 6 rules here. 6 rules we have. So any fuzzy model which is characterized by 6 fuzzy rules, and we have the rule number 1 as x1 is a, we have first rule as x is low, y is low, then the output is this, let's say this is Z1, and then the second rule here is x is low, y is high, then the Z2 is given by this expression. Similarly, x is medium, then y is low, and then this is Z3, this x is high, and then y is low, then the output here is for the fourth rule is Z4. Similarly, rule number 5 has x is high, y is medium, then the output is Z5. Rule number 6 has x is high, y is high, then the output Z6 is given by this expression. And the corresponding fuzzy regions that are given for low, medium, high for x input variable is given here, and similarly for the y input variable, the corresponding low, medium, high fuzzy regions are characterized by these membership functions. Now the task is here to find the corresponding output to x is equal to the input x is equal to 70 and y is equal to 60. So here the input remains the same, but interesting thing that we see here is that the connective is AND. instead of or. So here we have this connective. So if we have this kind of example, this kind of problem, so in the previous one we saw that we have had or as the connective. Here we have and. So obviously we are going to take composition as min. So let's proceed with this. This we have already seen as to how we can get this plotted. So here also for x is equal to 70, we have two intersection points. First is the for low and second is for high. Similarly, the y for y is equal to 60, only one intersection points. So the combinations again will remain same as the previous example. Now here we have to look for the applicable rules. So since we have 6 rules that are given for the fuzzy model, for the TSK fuzzy model, so we have only 2 combinations, that is low high, high high. So rule number 2 will apply and 6 will apply. This rule will not apply because the combination wise we low low doesn't exist, only low high exists here. So rule number 3, medium low doesn't exist, high low doesn't exist, high medium doesn't exist, and high high exists. How do we get this? I have already explained in the previous example, but I can do it again. So we see that x is equal to 70 cuts high fuzzy region here, high fuzzy region here, and then low fuzzy region, which is characterized by the membership, Gaussian membership function. So x and y we write, and then z. So x is cutting two fuzzy regions, low and high, and y is cutting only one fuzzy region here, the high. For others it is 0. So we can write LH and HH because high is for both the cases, and this way we have to look for the corresponding Z, and this we can find by looking at the set of rules, and we have here 2 rules that are applicable, and then with this we'll proceed same as we have done in the previous example. So now we see that here we get, when we take 2 rules, so we have to take only 2 rules. Other rules, rest of the rules will just discard. So because here rule number 2 and rule number 6 are only applicable. So we'll start with rule number 2. Rule number 2 is here. Now we apply the input x is equal to 70. So W11, let's say. Similarly here, this is W12 for the second antecedent, y is equal to 60, and then corresponding output here is Z1, and this Z1, by just substituting the value of x and y, we can have here, this is coming out to be 47. And now when it comes to W1, W1 will have min. Why min? Because here the connective is AND. So AND connective is used. So that's why we are taking min here. So if we take min of the two values W11 and W12, we get 0.0022. So we have here W1 and Z1. Now similarly, when we apply the rule 6 for the input x is equal to 70, y is equal to 60, we have Z2 like this. Z2 is equal to, this is already given, and when we use x and y, the values of x and y, we get Z2 here computed like this, 68.9, and the W2 is here, W21 and W21, and W2 2. So both are 1 here. So even if we take min is going to be the same. So W2 is the firing strength of the second rule, which is 1. So now we use these values here. So W1, W2, Z1, Z2, and then the weighted average is coming out to be 68.8519. So this way here we can say that the corresponding to x is equal to 70 and y is equal to 60, we are getting the output of the TSK fuzzy model as 68.8519. So I think we have understood now as to how we can compute the outcomes of the TSK fuzzy model in various cases for uh, various inputs and with different kinds of sets of the rules. And with this, I would like to stop here. Thank you very much.